Hello and welcome back to the Hyperthesis episode 70, which is gonna be the finale for the 5th season. My name is Pheely.
I'm Patrick.
And I'm Liam.
Alright, so today's main topic, which we'll get into, is gonna be about publishing and the scientific knowledge collectively as a whole, how things work, and why we do things this way as scientists. But before we get into that, anyone have the intro topic they want to talk about?
Yes. So I recently learned of a state of matter called a supersolid because they show up in ultra cold systems a little bit, which I'll talk about some more. But I basically wanted to talk about them a bit because what I usually do is I learn about something existing and I want to learn more about it. So I use this podcast as an excuse to go research it and then talk about what I learned. So again, I'm not an expert, but so it's this relatively new state of matter. Well, I guess experimentally new. Theoretically, it's been around. People predicted it for about 60-ish years now. So in episode 51, we had our guest Denise come and talk about her research, and we ended that episode with some history about superfluids. And I can't remember who told that story, but to quickly kind of summarize what a superfluid is, because before we talk about a supersolid, we should probably talk about what is a superfluid, because that's a bit more well known. Summarize that, starting back in the late 1930s, physicists discovered that if you take helium-4 and you cool it down to really, really cold temperatures, you get cool it down to around 2.17 Kelvin, so very cold temperatures. You get some weird behavior that you normally don't see in typical fluids. So when you think of matter normally, you think of like solid, liquid, gas, and maybe plasma, if that's something you know about. And we have everyday intuition about these states of matter typically because we've interacted with them. I've dipped my hand in water, I've held ice, I've seen after I get a shower, there's like steam on the wall. The three states. There's more moisture in the air. We know how these three states of matter work pretty well. But when things get really cold, quantum mechanics starts to become more important, and your intuition kind of goes out the window. So because of this really cold nature of superfluids, quantum mechanics is really important, and they do weird things that you wouldn't ever see in a classical fluid. Superfluids, since their prediction and theoretical advancement and experimental observation, they've been found to display really interesting properties like zero viscosity, so the ability to flow without dissipating or losing any energy. So if I had like a cup of water and I shook it around so that it was swirling and I set it down, the water would eventually stop flowing and it would come to rest. But if you do that with a superfluid, there's no friction, so the superfluid will flow in a circle for the rest of time, in principle.
Well, here's the thing. Is it a superfluid because it has zero viscosity, or the other way around, that is zero viscosity because it's superfluid? Like, which one is a necessary condition? Which one is sufficient?
Well, supersolids can have zero viscosity, but I'll come to that soon.
Well, but that's not fluid, right? So if it's a fluid,
but
can it be a superfluid without zero viscosity?
Yes, it can be a supersolid, for one. But
no, because can it be a fluid that is a fluid with zero viscosity, or without zero viscosity that is a superfluid? Still fluid.
Yeah, but supersolids aren't fluids, but they have zero viscosity. It's weird.
Yes, that's why I said if it's a sheep, it's like, oh no, it's a wolf. No, if it's a sheep, it's a super sheep, right?
Mm-hmm. Yeah,
so you can't just say it is a solid because the premise is a fluid.
Oh, I see what you mean.
You know what I mean? If the zero viscosity is a necessary condition for it.
I think so. Or pretty sure, yeah.
Yeah, because like if you define things that are superfluid by zero viscosity, all superfluids will have zero viscosity.
Yeah, there's probably more to it than that because a super solid's not a superfluid, but it has zero viscosity. So I think it's a
Yeah, but it's not
necessary
even a
condition.
fluid in the first place.
Yeah,
It's
I
not
know, but that's
fluid in the first place.
that's my point. Is that I think not everything with zero viscosity is a superfluid, but all superfluids have zero viscosity.
No, no, no. It's if everything that's zero viscosity and is a fluid, a superfluid.
Maybe, I
Maybe.
don't
Who
know.
knows?
Gases can be superfluids.
Well, gas is a fluid.
Yeah, exactly. Right. Like,
Yeah, but solid is not a fluid.
hmm but yet they can be superfluids. Anyway, um, yeah. Anyway, superfluids are weird. They don't display friction, which is extremely weird, for a fluid. But you can create them from, yeah, you can create. So I guess coming back to what you said a little bit, you can create certain kinds of superfluids from different kinds of atoms, either in a liquid or gaseous form. So like these Bose-Einstein condensates that I always talk about are these ultra cold atomic gases, which can sometimes be a superfluid. And this kind of led physicists to wonder, can a solid be a superfluid fluid? Which seems like a really weird question to ask because normally when you think of a solid, you might think of like a crystal with this really rigid structure that can't move. But it led physicists to seriously consider it because superfluid fluids kind of broke their notion of fluid, so they wondered if a super solid would exist. And but I guess before talking about like experiments and that, like how do you even conceptualize a super solid? Um, how do you have a rigid crystal structure of a solid combined with the frictionless flow of a superfluid?
Just to clarify our points earlier, it looks like superfluidity is the property of having zero viscosity. So yeah,
Hmm.
that's like you divide by that. So my guess, because like people usually think of solid as a rigid structure, right? But
Hmm.
that's not always true. Where if you look at under the earth for a volcano, for example, you have like magmas and stuff that's well, some of them fluid and rocks move, right? Even though it's much in a slower time span than what we have in a human experience, but uh, solids can move and maintain the structure. Like the could be a crystal structure or the solid structure, but it can still move even though it's a solid. So I want to hear what you have to say about
Yeah.
the
I think it's
super.
more so to do with superposition because in these really cold systems, like quantum mechanics is really important. So I think the intuition, from what I've read online and seen in videos and read in papers, the intuition is that it's possible to have a material consisting of quantum particles that are in a superposition of both a solid crystal and a superfluid at the same time. And this physicist said, imagine like a block of ice submerged in water. So the ice is like a solid crystal, but the water can pass through the ice at the same time. So it's like you have a solid crystal with friction with this superfluid flowing through it at the same time. It's in a superposition. I don't fully understand that, but I think that's kind of like the most basic intuitive way to think about it. Although that still confuses me a little bit. But it's very interesting that that's even something that can happen. So at first, physicists they said, okay, we found superfluid helium. Can you make super solid helium? And they tried all these experiments, and they thought they found it, but then they realized they didn't because there's all these weird things these weird properties helium has. So they actually don't know if super solid helium is real or not. People are still thinking about that. And many years since then, people have tried to create supersolids in different forms, but they were only able to do so in 2017. Two different research groups, one from Zurich and one from MIT, they used ultra cold quantum gases to create the first materials with supersolid properties. Um, so the Zurich group took a Bose-Einstein condensate and they put it inside two optical resonators which enhance the atomic interactions until they spontaneously crystallize and formed a solid that maintains the inherent superfluidity of a Bose-Einstein condensate. So that's a lot to think about. Um, And alternatively, the MIT group, they took a Bose-Einstein condensate. So both of these experiments were with these Bose-Einstein condensates, which I don't know what episodes we've talked about them, but many of them. Episode 51 for sure with Denise. So the MIT group, they took a Bose-Einstein condensate, they put it in a double well potential, so they trapped it kind of like in two dips, and then they shine light beams on it, and they created this effective spin-orbit coupling. So any physicists out there might know what that is. And the interference between the atoms on this spin-orbit coupled lattice gave rise to the characteristic density modulation formed by supersolidity. So I guess to summarize, they took Bose-Einstein condensates, they did some things, and they found things that looked like supersolids, but they couldn't definitively say they were supersolids. They needed to study how the excitations in the supersolids propagate to get like a definite confirmation that this is a supersolid. So for like a regular quantum solid, liquid or gas, excitations in them are called phonons. So when I talk, I produce sound waves, and the sound waves move out. Turns out if you have like a quantum crystal, you can get these quanta of sound. You get particles of sound wave called phonons, and they're little vibrations through the solid or the liquid or the gas. And they have, depending on what the material is, they have different types of phonons, their own characteristic signatures with their own special names. Typically, when you say phonon, you mean like a very specific type of sound wave. You mean one that changes linearly with its momentum. But there's different systems that have phonons that don't change linearly, and people give those special names. And we've talked about this before, but in 2019, so is when the actual like first definite confirmation of a supersolid was published. So 3 research groups, I forget where they're from, I forgot to write it, but they observed supersolid properties again in a Bose-Einstein condensate formed of lanthanide atoms. But this Bose-Einstein condensate didn't have the usual like collisional interactions. They also gave it dipolar interactions. So the particles could interact very far away from each other as well.
Sorry, you did write it down. It's Stuttgart, Florence, and Innsbruck.
Okay, I just accidentally forgot to read that. All right, the 3 research groups from those places. They took their Bose-Einstein condensate with not only kind of like contact interactions, so the atoms not only interacted when they bump into each other, but when they're really far away from each other, they feel a force as well. And that was one of the key properties. So they took this Bose-Einstein condensate, and the excitations in a dipolar Bose-Einstein condensate are called rotons, they're like a fancy phonon. They're very special types of phonons, and kind of my supervisor's, one of his more cited work is related to how you can create these in a Bose-Einstein condensate. He kind of came up with one of the first experimental proposals of that. So it's interesting to see that like supersolids, they always cite my supervisor, all these papers, which is kind of neat. The researchers were able to like tune these short range interactions on top of the long range interactions without the need for any external optical effects like the previous experiments. And they created supersolid like behavior. And additionally, the excitations that they found in the supersolid perfectly matched what the theory, well, maybe not perfectly, but very closely matched what the theory was. So that you get crystal excitations like you do in a solid, you get superfluid excitations like you do in a superfluid, and then you get these oscillations between the two of them, which accounts for the fact that the two of them couple together in some way. So this was kind of the first definitive proof for the existence of a supersolid state of matter. So I thought that was pretty neat. There's some other experiments in 2021 and 2022 where people created other supersolids with different materials, but they're not, I don't know too much about those, and I'm not sure what kind of applications it has. I'm looking at this and I'm kind of seeing like some analog gravity ones maybe, but I'm not sure.
A lot of like ultra cold quantum stuff is hard to relate to daily life because like those effects are basically fizzle out as the temperature gets higher, right? And those are ultra cold, which is really hard to get. So perhaps maybe more like scientific application rather than daily life applications.
Yeah, the big thing ultra cold gases are always used for is kind of understanding basic physics and then using that understanding to help develop more realistic systems. So if you can, I know one thing people do is they create they use optical lattices to create kind of like crystals of ultra cold gases, and then they can understand the really basic physics because there's not really much thermal noise, and they're really simplified compared to, say, like a solid state crystal. And then with that understanding, you can now kind of better understand how a crystal works, and then you can use crystals to make all kinds of things like semiconductors and blah blah blah. So a lot of ultra cold physics is just understanding fundamental stuff and then using that to understand a more complicated system better. And that more complicated system probably has more realistic applications. But I think superfluid helium actually has some legit applications. I don't know if they use it, but in like LIGO, for example, for these gravitational wave detectors, they have these really, really cold mirrors and I think they're cooled with superfluid helium, although I'm not sure. It has some more as well, but I just don't know off the top of my head.
I'm pretty sure they are cooled because they have to keep quite cold to limit their motion and additional vibration from thermal activity. But that's really cool. And just even just seeing it in writing, like a super solid quantum gas, like a solid gas, is just a weird idea to wrap your head around. It's cool though.
I think there's better intuition than what I have, but the best I could come up with is that it's just in a superposition of superfluid and solid, which still confuses me a lot, but it's not, at least I can just blame quantum mechanics for not understanding. I can just say, it's weird.
All right. Then thank you, Liam, for the intro topic. So shall we move on to the main topic today, which is on about publishing and such. I think, it's some topic that is not exactly directly related to science, right? Because this is almost like another field or another, well, everyone that's gonna go to academia want to publish has to deal with it. And I feel like most people have their own idea of how the publication and the system work, and I want to hear what people think.
Before Patrick starts talking about it, I just imagine that all three of us, our viewpoint is like publishing and science. So I think all of our opinions and what we say is heavily biased towards that. Like, I don't know how publishing in the field of history works or the field of sociology or anything. I just know how it works in physics and a little bit about the other sciences.
Yeah, I mean, in all academics, publishing is very similar, but it's just a little bit different in terms of the content and also the process that's taken. So, for example, for history, you might see more textbooks relating to history than you would, say, in physics. But a lot of people still have to go through this, no matter where you're coming from in academics. And so today's topic will focus on this specific topic of publishing, specifically in science, just because that's what we are familiar with, but I'm sure there are some broader applications. And it's more so, rather than looking at science itself, like what we usually do, how we actually convey that science. So how we convey this knowledge that we've gained, whether looking at supersolids or superfluids or really anything under the sun or including the sun or orbiting around the sun, who knows? Because we want to make sure these discoveries that have been made are sound, that they're verifiable, that they're fact-checked, that they've gone through a rigorous process, which some might call the scientific method, and others just try and stay as rigorous as possible to that. But this allows them to be published and adding to a collective body of knowledge in whatever field in which they may be relevant. So this is true in medicine, mathematics, engineering, and just all of the sciences, whether you're in physics or environmental sciences, biology. There's a whole process for publication that's an entire other aspect of science itself, and it's becoming increasingly important to know how to essentially kind of calibrate your work to be better publishable and make sure that you have good results so that it's more publishable, that your data is very extensive but easy-ish to understand depending on what you're doing, to make it so that when you do publish it, others can understand it easily. And this centers in the modern day around the idea that every scientific paper that's published undergoes a peer review to ensure its validity and integrity before it enters the public domain. And that's not the same as the copyright public domain, it's just out there in the open for anyone to read. And the idea of peer review and of publishing in journals has changed greatly. And I think it's important to provide just a bit of context and background to where we are today about publishing. So as a quick history lesson, in the beginning, it was very difficult to get something published. If you're a grad student right now, you might be thinking, oh, well, it's really difficult to get things published today. It was even worse back then. Essentially, if you weren't a man who had money, good luck getting something published. And it truly did depend on just either having money or knowing people with money who would invest in the printing cost for whatever you wanted to be printed. Now, back then, the printing press was relatively new compared to today, and organizations like the Royal Society were able to gather funds based on membership and other means, and were able to actually print these different scientific articles at the time and books, and even the first journal, which is still around today, and it was known as Philosophical Transactions.
Well, I think it's important to talk about what exactly is like publications doing, right? Because they basically want to promulgate the information to people or to other academics, and that's usually go through the libraries. And how it works, I think, like most universities now still have subscriptions to journals. And back in the days before the era of the internet, they would have to print a lot of copies and send to every single library that subscribe to. That's why if you look at how much universities actually paying those journals, I think it's thousands of dollars per journal, because maybe it's different now, but to gain access to everything and the system is this elaborate thing where, it's such a hassle to try to share it to everybody and make sure the information is correct and consistent, so everyone can talk and collaborate in the same field.
Mm-hmm. And those systems just were not really in place back in the 1600s. I mean, it was difficult to get anything printed unless you knew someone. And even then, if you had a brilliant idea and knew people, they had to have money. So a fun little thing, which we'll be talking about possibly in the story, is that the Royal Society actually published a book called De Historia Piscium, which roughly translates to the history of fish. And this was supposed to be a huge book. They would sell it everywhere. And they essentially used a lot of their money to print this book, and it failed. It was a huge flop. Shortly after, Newton came with his Principia Mathematica, or Philosophiæ Naturalis Principia Mathematica, which is his huge book that talked about the laws of motion, and pretty much a founder of classical mechanics. This was the book for it, and they were like, oh, we don't have money for that. So it was actually Edmund Halley who published it. But again, it's because Halley had money, and Newton was fortunate enough to know a guy, essentially. And this kind of thing lasted for centuries, where people could publish their findings if they wanted, but they had to know the right people, be in the good books of the right people. Some journals would be controlled by one person, and if that person liked you, then you would get your stuff published. If not, well, too bad. And so there were many disputes and biases. For example, see the Newton versus Hooke for some drama if you want. But there was really no official standardized way to get the word out about research, other than just hoping that if you wrote a letter to someone, they might print a portion of it and hopefully not steal it. And peer review in itself was not something that occurred and was really just something that hasn't come about until really the middle of the 20th century, which is quite recent in terms of the body of knowledge that we have.
Well, most of human history, one of the biggest problem we have is long distance communication, and that is like up until the telephone or the telegram, right? That has been extremely difficult, and well, they can to do it with letters and such, but it takes a long time to write a letter to someone. Let's say in Europe, and you're in another country, and hey, there's a letter. Take a few months to get to this person, and hopefully it gets to that person. Well, may not be very reliable, and then it take a few months for that person to send it back, and the development of ideas. So it takes time, right? And now it's completely different, where we have all this technology to assist us. That I think that's one of the reasons we see a huge increase in productivity in terms of science and the scientific progress.
Yeah, and so peer review has a lot of thanks to that because we're able to actually send papers to experts around the world. And in the 1950s, you could better send that through established mail systems or maybe telegraph. That might be pretty difficult to send an entire paper through telegraph. But the idea of these peer-reviewed journals is pretty recent, but it's also very useful because then you get that validity checked of your work and you don't have things slipping up like, for example, recent controversy around the LK99 superconductor, which was supposed to be a room temperature superconductor. Probably not.
Well, the internet itself was created for, I think, physicists to share papers and such, if I remember correctly. Like it's as part of like the university system, so they can share stuff. And it turned out it's very useful.
Yeah, I believe the internet was created at CERN, essentially for people to communicate better and pass data along better. And I mean, it's really helped journals gain momentum. However, in the 1960s and 70s, a lot of these journals, with like Nature or essentially any journal you can think of, was privately controlled, but as a nonprofit, open organization. So they would take in funds and then they would publish. Now, commercial publishers started paying attention to this and buying up these different publications. And as of 2013, which is a little bit outdated, but 5 major publishers controlled about 50% of the scientific articles that were released. And these 5 are Reed Elsevier, Stringer Nature, Wiley Blackwell, Taylor Francis, and Sage. And now keep in mind that these are commercial publishers, they are for-profit companies, and on average, they have a profit margin of 40%, which for any business is quite a high number. And the fact that commercial publishers exist have been debated, and the idea and the concept of for-profit publishing is only getting worse. Prices are going higher and higher as budgets are being cut at universities. And having a paywall for knowledge that should be truly open access, because it's work that's being done by people to contribute to the body of science, and then putting it behind a paywall where you have to pay tens to hundreds of dollars just to access it, has led to something that's known as the serials crisis, which is this problem of journals are asking for a lot of money, people are having less money, researchers and institutions have less money. And it was found, especially by Deutsche Bank, that these companies were not adding significant value to the process of peer review and publishing, especially to account for this 40% profit margin.
Well, there were those predatory journals too, right? That's one thing that we were taught to avoid, because the people that say, "Hey, come publish with us," and things are too good to be true. And there are 2 ways, right? Usually there's some open access. Usually, if you want to publish that's accessible to everybody, you usually have to pay for it. And if you want to publish for free, the readers have to pay for it. So it's a money game all over again. And there's this idea that knowledge of mankind is like an island that the scientists contribute to this island of knowledge, and it get bigger, and the borders or the borders get bigger, so there's more to discover and such. It's a fun idea, but that doesn't reflect the reality of publication. That when publication is part of the system, where it's basically, I heard about this from somewhere. It was probably like a craft of writing effectively, because I was talking to my colleagues and the supervisor, and one of the ideas that, well, we're not, usually when you do PhD, you think you're gonna do some novel thing or something new, something that never done before, but that's not really true. Well, that's not what it's about, because we are not get paid to do novel work. We get paid to do valuable work. So it doesn't matter if it's new. Is it valuable? That's very important, because you have to convince people your work is important and is valuable, not because it's new. Just because it's new doesn't mean it's important, right? So that's part of publication. And what happens with this is like the knowledge of mankind is like a blob that floats in time, right? It might get bigger or smaller. And they're these gatekeepers, where back in the days, usually those people look very similar and of the old age to gatekeep all the knowledge, all the papers, because that's from the journals. They have to review it. They don't believe in your theory, they won't publish it. And if they won't publish it, it's not going to be part of the knowledge blob that traveled through time. So that's the job of the scientist to us, is to challenge that blob and say, hey, you did good work. This is how you can improve it. Or this part is maybe wrong, and here's why. You challenge that blob. You challenge the status quo and try to convince the gatekeepers, which are the maybe now it's peer review, it's editors, to convince them that your work is worthwhile and is challenging, it's enough, and is worthy to be part of the knowledge blob.
You hit on a really good point there, and that's showing that your work has value. And I think beforehand, for the past couple centuries, it's shown that it has value in that, one, it may go with the flow. It might not be this kind of paradigm-changing paper, but accepts previous work and then supports it. Whereas nowadays, that value is more of a commercial value. So these large journals like Nature, Scientific American, or other journals like that, instead of looking at necessarily the value of the science itself and how well done it is, it looks for the commercial value. So something about Nature is that, which for those who don't know is, I would argue, the largest science journal. There are a bunch of different Nature subjournals like Nature Communications or different ones like that. But essentially, if you want to publish in Nature, it's beneficial not to have published with them before, but to have a paper that's unique and novel, meaning that it's more likely to get commercial value. So more people are likely to pay Nature to buy this paper, whether to view it for 24 hours, which is a thing with these publishers, or to keep it. And it might be several $100s, especially with something like Nature. And then it's also valuable for journals like Nature, Scientific American, or really any journal, to increase what's known as their impact factor. And now this impact factor is on a scale, so can be as low as 0 up to technically an infinite amount. But based on what I know, I think it's like the average number of citations per paper within the journal. And so something like Nature has a very high impact factor, and they want to preserve that or increase it as much as possible. So they get quite sticky with what is actually accepted in Nature. It has to be quite novel, and it has to almost be guaranteed that it's a success. But by being published in Nature, it also kind of guarantees that it will be a success. So there's this kind of commercial and self-interested impact that allowing certain research into a journal has on the journal itself. And like you said, it's kind of being gatekept in the way that there's very specific criteria and specific research that these different journals are looking for.
Yeah, one of the problem with the impact factor is that, different fields would have different maturity rate. For example, if you publish something in relativity, you might not get cited a lot, and also it might take some time to get cited because if you do a lot of like theoretical work, it takes time for maybe other groups or other people around the world to catch on and and see these ideas, and might take a few years to even develop it compared to, let's say, like experimental work where a lot of groups would do multiple experiments at a time, right? And you can test and develop your bunch of papers out that have a lot of citations. So the impact factor, I mean, is a parameter that can tell certain things for the paper, but it doesn't directly speak to the quality of paper. You can have a lot of highly cited paper that might not be as good. It's just who knows, like maybe something that's like hot at the time in the news, and you publish something, it got cited a lot, but could turn out not to be true or get disproved.
Yeah, even with like that example of supersolids I was talking about earlier, the theory people have been doing the theory of that for 60 years, and they only made the experiment within the last few years, right? So that's pretty common. Or one example is quasi-crystals. Well, I don't know about citations, but I know that like going with the flow is the safe thing to do, which might get you a lot of citations, but doing something novel, which people might dislike in the long run, might be better. So I forget the name, but whoever quasi-crystals are, they're crystals that don't display the same periodicity as kind of regular crystals. Because regular crystals, you have like a crystal lattice, so you might have a hexagon, and then you have all these repeating hexagon patterns everywhere, and that's what makes it a crystal. Quasi crystals don't have, I can't remember if they don't have periodicity or they have like specific non-novel periodicity. I don't remember, but anyway, the first person to claim to discover a quasi crystal, he made a publication on it, and people just like clobbered him. Like he got like, it wasn't just like Pete telling him they're wrong. They're like, he was like fired from his university, and publication was revoked, and like they're like, this is impossible. There's no such thing. And then of course, years later they found out that wow, this is real. He was right, and then he won a Nobel Prize for it. But it took like many many years for people to even accept his idea. So I'm sure like journals wouldn't take his publications, things like that. So it's crazy how some of this stuff works sometimes.
Yeah, it's I think it's more common to hear about those kind of story now, where like, oh man, I discovered this a while ago, and they wouldn't believe it. And here's the thing, right? The amount of papers we see is on the surface because it's those that published. There are a lot of ideas that they're literally just got shelved. Like in my group, for example, I think there are multiple ideas that didn't come to fruition. I think there were good ideas that sometimes like the student finished, didn't have time to work on it, so they shelved it for a while. And maybe in a few years, someone will come along and continue that idea. What I'm doing for my PhD is basically continuing from this idea, and I'm basically rebuilding the everything, right? So it's interesting how much of like the iceberg, there's so deep the things that ideas that never come into light. So it is what it is.
Yeah, I mean, I have a lot of ideas that I have not acted on yet, and hope to do before I die, but we'll see.
Or even
But
those that already written, like done, but not published.
mm-hmm. Oh, okay, yeah, because you might get, so this is kind of related to that. It's something I wanted to comment on. Was like back in the day, you were saying you needed to know the right old rich guy to sometimes get published, and even though today with modern journals it's way better, you have peer reviewing, you have preprint journals, which I think you're going to talk about shortly. You can still, people can just not like your paper and not publish it. So me and Pheely and our other friend, who was a guest dean, we're publishing. Well, we're gonna try and publish a paper soon, and this is the first time, at least for me, that I'm trying to publish a paper without like an established physicist helping us with it. So we're kind of going into it, not blind, but inexperienced. So I talked to my old supervisor. I had a Zoom call with him to try and get some advice from him, and he was telling me about this one time he tried to publish in a journal, and the two referees he had, so the peer reviewers, they just didn't like his publication, even though it was perfectly sound, even though it was actually like a pretty useful thing. They just didn't like it because it kind of went against what they believed in. So they're like, no, like this is bad. You have to change it. You can't do this. And then he went to, a more he went to a more respected, more reputable, harder to get into journal, and they loved it. They're like, the two reviewers were like, yeah, like this is great. Like we'll take it. No revisions necessary. So even though things are better today in the modern world, you still get that stuff often, and you hear this joke where it's like your first reviewer will give you like pages and pages and pages of comments, and the second one will just be like, yep, looks good.
Well, and that's the thing, right? Like when you publish or when you try to publish your paper, you send it to the editor, and that's the first gate, right? Where the editor would look at it, it's like, oh, does it fit the journal? So, well, and to whether it's to send it to reviewers. So if the editor said, hey, I don't think the journal fits, or I don't think it's true, I think like more than 90% that the papers that got into like the big journals got taken down, or not like got refused, not even reach the reviewers, right? Even reaching the reviewers is also like most of the time, or sometimes I think most of the time you don't get to choose your reviewers, and sometimes it's anonymized too, so you don't know who's reading your papers, and it could be someone who doesn't believe it at all, or may have a good argument as to why they don't believe it. And I think it's a good thing, right? It's peer review, but sometimes it's just like they just could not believe it at all, and it's a little bit of luck to get published.
Yeah, exactly. And there's actually there's ways around it now with preprint journals, which, depending how you look at it, are good or bad. But I will leave that to Patrick. I'm sure he has some things to say about it.
Yeah, so preprint journals are a way to circumvent this idea of you have to wait weeks or months or years for some reviewers to take a look at it and maybe accept your publication. And these circumvent it by allowing you to pre-print your publication before it undergoes peer review.
I know there's this really popular one in physics called the archive, and I'm pretty sure it was either originally developed to speed up the process, because with the power of the internet, people were publishing and finding new things way faster than journals could keep up, and they didn't want to, everyone wanted to discover the next Nobel Prize winning thing. So instead of just waiting up 2 months for their one publication to go out so that they could produce a second one, they would just throw everything in this preprint journal, let it be kind of open access, and let physicists review it and send comments as they wish. And then with the understanding that eventually it's going to get peer reviewed and published in some journal. So I think that's why. Or it was because another reason is because of gatekeeping with journals. People wanted to publish things, and just because a journal didn't like their publication, they thought it was worthwhile. So in the archive, you could publish it, at least originally. I don't know about now, but you could publish it whether or not it got peer reviewed.
Yeah, so the archive was founded in 1991 at Los Alamos National Laboratories. And there was actually a really nice piece done a couple years ago in a German newspaper about the inventor, who was German. And just about the kind of revolutionary idea that it was, where you could put things up right away. And mind you, they weren't peer reviewed, but they were a way to get the knowledge out faster. And like what we talked about, where they might be rejected from papers for unknown reasons or for biases within the selection process. So now Archive is based out of Cornell University, but since 2004, it has required authors to either be registered or have endorsements to be able to publish it. So this is a new level of restrictions. So it's not completely open access. You need to essentially know someone or be that someone to publish in the archive.
And that's ARXIV for those wondering if you want to look it up.
Yeah, almost all of these systems use an X, well, or the Greek chi in it for chive, like archive. And so in this case, yeah, if you look up any of these preprint journals, they'll all have this X in them. But going back to archive, this moderation process is interesting because now it's limiting the idea of open source publishing so that anyone could publish. And it really does harken back to the days of, you kind of had to know someone. And those endorsers that archive has might play it safe, because if they allow something to be published on archive that's not really sound or scientifically verified, then they might get their position of endorser revoked, and then they might not be able to publish on archive as well. So it's also turning into not the most friendly place for anyone to publish their findings. And so other preprint servers have popped up, like Vixra, which exists and pretty much accepts any submission. So this is nice because it opens the door. It doesn't have the same gates that archive has and the same number of processes that you have to go through. But on the other hand, this opens the door for a lot more to be published there, and these might not all be scientifically sound.
Yeah, Vixra is just archive backwards. So it was kind of a dig at the archive for putting in more restrictions, because it's like it's an interesting gray area, because more restrictions means things are slower, and not just that, but yeah, you can get gatekeeping that is not necessarily good. You can get bad gatekeeping. But also with Vixra, like you say, you can get some unscientific things in there, because anyone can publish in whatever they want. There's no peer reviewing or anything. And usually I guess in archives early days where there wasn't any requirements, you could just publish. It was kind of like up to the science. It was up to the people reading it to have the kind of common sense, and well, not common sense, but like the knowledge. Like it was up to the readers to peer review it themselves and go through it and say, does this make sense? Is this legit? But in such like a connected world now with the internet, you could get one publication that says like cats can fly, and people will just see it and blindly believe it. So there's this danger with Vixra, which is why a lot of physicists, I remember during my undergrad research, I found this publication in Vixra, and I had no idea Vixra was like a play on archive. I didn't even clue in. And I was like, it gets this like really, it has this stuff I was interested in. And I went and I showed my supervisor, and I said, there's this paper that does this. And he's like, it's published in Vixra. Like, don't trust it. Just immediately he's like, if you believe it, replicate it yourself, but just don't inherently trust it because it's in Vixra. So it's this double-edged sword.
This idea of the fringe science, right? That is on the fringe, it's not true. And I think, what I heard at Vixra is like some people who got kicked out or banned from the archive go publish there. So if you, like a normal person who want to publish, you or do the preprint, you would go to the archive, especially in physics. And if you had to go to the Vixra, that's probably a good reason why they had to do that, right? And it's gatekept a little bit, but still, in terms of compared to scientific journal is way less, anyways.
Yeah, like quote unquote good physicists will take the precautions and make sure that their work is justified and it's not just a bunch of nonsense before they go trying to publish, which is why I haven't published this paper we've been working on yet. I've been double checking it and triple checking it and making sure it makes sense, and I'm trying to make it like readable, and because you don't want to just like have an idea and blindly publish it in the archive, because like it could be super wrong. You could have missed something really obvious, right? And then you lose your credibility. So I guess this Vixra it's people who just publish in it, they either don't like the archive or there's probably a reason why they're publishing there and not the archive. And then, subsequent after the archive, like an actual peer-reviewed journal.
Or they could be publishing in both just to get a wider spread. Because the thing about all of these preprint services is it creates what's known as a digital object identifier. I think that's what it stands for.
DOI?
Digital object identifier, or DOI. So you're actually able to access this officially. And I mean, I've seen papers that cite papers that are in the archive, but they can also exist in the archive. They can exist in Vixra, and they can be published as well. The thing with being published is you can't make any edits to it, whereas with archive, you can actually do that. And every time you add additional edits, it will produce a new DOI, which can also get confusing because if you've submitted it for publication, but you've also posted it on the archive or on Vixra, then there will be essentially different sources for the same information. And that can get confusing, especially when you go to cite that source, because some people might cite the archive because they didn't realize it was published, or it might be cited in archive before it's fully published and then later on cited differently. So that can also lead to some confusion in terms of citations and references.
Yeah, the general rule of thumb is that if it's in the archive but not published, you reference the archive because it's there, with the understanding that, you've checked it or it's pretty sound. But then once it gets fully published, if you're going to cite it again, then you properly cite it. But sometimes I've seen like you get some sloppy citations where they've cited something in the archive that's published somewhere and they just never checked or something. And the thing with Vixra too is that like I've never seen anyone cite Vixra because it has negative connotations with it, which probably rightly so. But if it's no one cites it because they don't want to look like fools.
Well, one thing about the preprint like archives that sometimes the paper you want to read is under paywall, it's behind paywall. So, but sometimes it's available in the archive, so you can see possibly the earlier version, maybe unedited version of the paper, see what the idea was about. But sometimes the journal actually would not allow you to publish in the archive on the preprint because they don't want they want to keep the paywall up so it get paid.
Yeah, every journal's got their own beliefs. Some journals, especially like Nature and stuff, I actually haven't explicitly checked this, but I'm just assuming. A lot of journals don't want you publishing in the archive because they want people to pay to look at your publication. Open access journals, like the IOP ones, they don't care if you publish an archive because they're open access anyway. But then you get some, like I think American Physical Society, they have a paywall, but they also don't care if you publish in the archive. So there's a bit of, depending what journal you go to, they have different opinions and different rules. So you have options, but then the hard part is getting them to accept your publication, of course.
All right. Well, I think there's a great discussion of publication and such. So, I'll get Patrick to tell us, unless he has a lasting comment, final comment to tell us how to reach us.
Oh yeah, so I have one more comment about archive versus Vixra because again, it's like a gray area. Like I think it's important that people can publish what they want. So I think Vixra has got kind of, I like believe in it a little bit, but I don't at the same time because I think them taking a dig at archive is important because archive kind of became that it started off open, now it's a bit more gate kept, and you need to know the right people and you need to be endorsed, and if people don't like your research, even though it could be legit, you might not be able to publish there, and that's bad. So Vixra, like, I like that idea of it, but at the same time it's bad in the sense that you get a lot of pseudoscience and people who just publish there because they know they can and they know no one else is going to take them, or people have rejected them for not doing sound science. So I think the take-home message is be careful out there and double check your papers when you read them.
Absolutely. And I just want to say that the work we do today as scientists relies a lot on information from the past and discoveries from the past. And I mean, the quote, "We stand on the shoulders of giants," is prevalent. If you go to Google Scholar, right on the front page is "Stand on the shoulders of giants." However, with everything going on with journals and publications and the increasing cost and commercialization of everything, it's becoming more difficult to stand on their shoulders. And so those giants are becoming increasingly inaccessible and further out of sight. And with that, if you have comments on the idea of preprints or publishing, or if you just want to air your woes about trying to publish a scientific article, if you're a scientist in the field, there are a couple of different ways you can contact us. The first is our email. We are found at hyperthesispodcast@gmail.com. You can send us an email if you would like to suggest topics for upcoming seasons. This is the end of season 5, but we are going to be starting work on season 6 in not too long. So you can reach out to us there, and we are also looking for guests. If you are an expert in your field, we would love to have you on. If you don't want to contact us via email, you can check out our Instagram. We are Hyperthesis Podcast. No, we are at the Hyperthesis, and you can send us a DM. You can also check for updates, especially when we are back up for season 6. We are on YouTube. You can watch our full episodes there. We're pretty much caught up with everything, thanks to Pheely and his powerful MacBook running all the processing. And you can also leave a comment. You can like, you can subscribe, and you can, I believe, send us a message over there. If you are listening to us, congratulations, you found us. We are based out of Spotify, but we are pretty much on every podcasting service imaginable. And I actually have the list in front of me today. So we are based on Spotify, Apple Podcasts, Google Podcasts, which will soon be YouTube Music, Amazon Music, which I believe is now Audible, Overcast, Castbox, Pocket Casts, Radio Public, iHeartRadio, Stitcher, and as more become available for us to upload to, we will try and expand. So make sure to share us, get in contact if you'd like, and give us a rating, comment, subscribe, do whatever you need to do to give us a listen and share the word of the Hyperthesis.
All right, thank you, Patrick. And we will move on to the story.
Yeah, so for today's story, it's going to be a short one, but it's relevant to what we were discussing today. And that's the idea of an ancient, we'll call it a tome that was published several hundred years ago. And its title is Philosophiæ, Naturalis, Principia, Mathematica. Otherwise known as Principia, it translates to the mathematical principles of natural philosophy. And the author of this work, or I should say set of works, is Isaac Newton. And this is the book in which Newton describes, Newton's laws of motions and laws of gravitation. And it was first published on July 5th, 1687. Now, it is completely in Latin, much like the title, and this was done by Newton to kind of gatekeep the information held within, so you actually had to speak Latin to be able to understand everything. And this book was published across 3 different books. So book one is De Motu Corpum, on the motion of bodies, and it concerns the motion in the absence of any resisting mediums, like the atmosphere, and it essentially describes how things move. So, for example, it looks at things such as Kepler's laws and relates circular velocity and radius to path curvature, or radius of path curvature to a radial force, and essentially does a lot with the motion of objects. Now, the second part is Book 2, which is just part 2 of De Motu Corpum. Apologies to any Latin speakers if I pronounce that wrong. If you exist, please let us know. And here it discusses resistance in direct proportions to velocity, hydrostatics, so it adds in some more realistic conditions to those ideal laws of motion. And finally, the third book is De Mundi Systematae, or On the System of the World. And this is an exposition on the many consequences of universal gravitation. So this builds up this law of gravitation, and taking information from the previous books really builds on the ideas of orbital motion, variations within it, and really goes in depth with orbital mechanics. Now, I wouldn't get too much more into what the book is about. You can go find it, or at least translated versions of it. But what I really want to talk today about is how it was published. So in January of 1684, Edmund Halley, Christopher Wren, and Robert Hooke, which I'm sure you are familiar with those names if you've been listening to our podcast long enough, they had a conversation in which Hooke had said that he derived the inverse square law, and also all laws of planetary motion. Now, Halley and Wren were a bit skeptical of this and said, okay, show us. And the thing is, Hooke never did. And so now it became a challenge to see who could derive the inverse square law. Of course, it wasn't called that then. And Halley was able to do this for the circular case, and he did this by substituting some work from Kepler and Huygens for centrifugal force again. I wouldn't talk about this too much, but he went to go ask Newton because he knew that Newton was quite the genius. And so in 1984, Halley went to visit Newton and talked to Newton about, okay, how would this work? And Newton, of course, being the genius he said, okay, yeah, I've got it. And this spurned the actual idea to write this Principia, as it's commonly known as. So Halley at the time was a fellow and a council member of the Royal Society in London, which is a very well-respected position. And when Halley asked Newton's opinion on the problem of planetary motion discussed, Newton said, hey, I've already done that derivation, and went to go find some papers and showed them to Halley saying, oh yeah, this is already been done, which I mean is a power move, if anything, saying, oh yeah, I did that years ago kind of thing. And so the work that Newton had done took the form of a 9-page manuscript called De Motu Corpum in Georum, which means on the motion of bodies in orbit. And although there are some surviving copies, the original doesn't actually have a title. Now, Newton's idea of the motion of bodies was later expanded based on encouragement from Halley, in which he was able to extend the methodology and add solutions to problems of objects traveling through a resistive medium. So think air resistance. And based on this, the Royal Society wanted more of the work. And so this encouraged Newton to keep working and working until he finished the last of his computations and calculations in mid-1686. Now, this was great work by Newton. However, as I mentioned earlier in the episode, he went to go print this giant tome of a book, which was eventually split into 3 different books, and was met with a no from the Royal Society, who had spurned him on. And that's because of the publishing of the History of Fish, which essentially used up all the funds for the Royal Society, and so Halley actually had to front the cost. Now, I'm sure had the Royal Society known the impact that Principia would have, not just for a couple of years, but for centuries, they might have been more willing to part with their money. But now Halley gets the honor of having paid for the publication of such a important book. And so it's Halley that we have to thank, along with, of course, Newton for actually making the book, that we have such a well-known and well-understood tome and understanding of classical physics. Now, it's interesting because Halley financed this publication, and then he was informed afterwards that the Royal Society could no longer afford to pay him his promised salary of £50, And so instead, Halley was paid in leftover copies of the history of fish. So it's important to give people a chance and, in my opinion, to have very open access publishing. So the next Newton, should they come along, has an open door to getting their ideas and thoughts published. And much like Halley, we need more people that are willing to donate money and support scientific research going in the right direction, even if it's a different direction.
That's pretty rough, getting paid in the history of fish books. I wonder how many they gave them.
It's a good question.
All right. Thank you, Patrick, for the story. So this is going to be the last episode for this season, and we'll be taking a break, and we'll come back in due time. Thank you, everyone. I'll see you next time. Take care.
Bye, everyone.
Thanks for listening.